All right, take 92. All right, so here we go. This is your third and final video on the relationship between work and energy. All right, so what we're going to learn today is about how work done by non-conservative forces affects the energy of the object. Before we do, a quick side note that is really not that big of a thing, but it's something I should point out. So up until now, I've always told you that total energy is the sum of kinetic energy and potential energy. All right, that's a little bit sloppy. What I really should be doing is I should be calling this mechanical energy, because there's another type of energy which is called thermal energy, sometimes called heat energy. All right, and so when we talk about total energy, what we're really doing is combining the mechanical energy and the heat or thermal energy. And the idea is, up until now, I've just been kind of ignoring this because it hasn't really been an issue. And honestly, I'm going to continue to do that unless there's a question which specifically asks about thermal energy or heat energy. And if that's the case, there's a really easy way to calculate it. And I'll show you what that is in this video. Okay. So I'm going to try my hardest in this video to talk about mechanical energy. All right. And when I say mechanical energy, you should think, oh, that's just the combined potential and kinetic energy. Okay. What we have previously called total energy. All right. This is really such a small issue. It's just learning this new term. Mechanical energy is what we used to call total energy. And I apologize. And if it wouldn't take me literally hundreds of hours of work, I'd go back and change all of them. But I have so many solutions and videos and stuff that I've done using total energy that I just frankly don't have the time to go back and change everything. All right. So small inconvenience for one type of problem. All right. So here we go. So work done by non-conservative forces. So we already know that if our non-conservative forces don't do work, then there's no change in our total mechanical energy, right? Okay. That's conservation of energy, right? That if there aren't conservative forces doing work, then the total energy, mechanical energy stays the same. So it turns out if the conservative forces do work, then the work done by the non-conservative forces is your change in mechanical energy. So the work done by non-conservative forces is the change in mechanical energy, which for us is change in kinetic energy plus change in potential energy. Okay. So for a practical sense, so if I take an object, so right now, let me make sure I'm in the calendar. So here's this coffee cup. Right now, it's got a little bit of energy. Now it has more because I did work. So if I did, say, 10 joules of work lifting this thing, then I gave it 10 joules of energy that it didn't have previously. Okay, so that's it. All right. So how does this tie into all the equations? Let's kind of run through all of our work energy relationships. All right. So net work is the combination of the work done by non-conservative forces and the work done by conservative forces. All right. So let's think about what each of these elements mean. So here we know that our net work is our change in kinetic energy. I don't like how I wrote that. Our net work is our change in kinetic energy, right? So I'm going to go through and I'm going to substitute each of these. So this becomes change in kinetic energy equals, well, let's see. The work done by non-conservative forces, so equals, the work done by non-conservative forces is our change in mechanical energy, formerly total energy. And then our work done by conservative forces, remember, the work done by conservative forces is the opposite of our change in potential energy. That's what the U means, okay, potential energy. So this is minus the change in potential energy. So look at that equation. So if we add the change in potential energy to both sides, then what do we get? Well, we get change in, we get change in KE plus change in PE equals change in mechanical energy, which we already knew. So my point is this equation agrees with this equation and everything works out, yay physics. All right. So this is just this guy. And I guess the only equation on here that we didn't talk about yet is this dude right here, which just says that your network is all of your works added up. So the work of Roy, plus the work of Sally, plus the work of friction, plus the work of gravity, plus the work of normal force, plus the work of the spring, plus the work of the fact that I dropped my pen, was all added together, give you your network. All right. This slide is colossally important. All right, because this is what ties together work and energy. This whole chapter is working with these relationships and then remembering that work is the integral of force with respect to position, or more commonly, usually our forces are constant. Work is force times displacement as a dot product, right? And remember, we learned 4 different ways to deal with this a chapter or 2 ago, all right? And we did that work basics stuff. Okay, so we're going to apply all of this here in the video today. All right, so we're going to solve 2 or 3 problems using this idea here. Okay, that the work done by non-conservative forces is our change in mechanical energy. Before we do, let's talk about this real quick. So, friction. Do you know what? No, I'm going to do this at the very end. Final. Look at me making a game time decision. So it's my last example. Yes. All right, cool. All right, so let's do an example. Bam. There we go. All right, so here we go. So let's do an example. So the whole premise behind this example is going to be that the work done by non-conservative forces is our change in mechanical energy, which for us is our change in kinetic energy plus our change in potential energy. That's at the heart of this example. All right, so here we go. Roy pushes a 40-kilogram box up a ramp that's 5 meters long and 3 meters tall. There's a ramp. So the problem tells us that it is 5 meters long, 3 meters tall. That means this last side here is going to be 4 meters. Here's the box. It's 40 kilograms. It doesn't explicitly say it. Let's assume that it starts at rest at the bottom of the ramp. And what we're trying to do is find the final velocity at the top of the ramp under the following circumstances. All right, so first of all, let's see. It tells us that Roy uses a horizontal force of 700 newtons to push it off the ramp. So let's go ahead and draw that in. So here's our force of Roy, 700 newtons. Let's see. Then it tells us that the force of friction between the box and the ramp is 140 newtons. That's going to be down the ramp. That's kinetic friction, isn't it? 140 newtons. What other forces are there? There's gravity. And normal force. And I think that's it, right? Now, I could, if I wanted to, split all these forces up into components and calculate my normal force. But really, the only reason I would need the normal force is to find my friction. But we already know that because I gave you the force instead of the coefficient. All right, so I think the other thing that we probably need to point out here is, let's take a look at our displacement, because our displacement vector has 3 components. So the actual displacement is along the hypotenuse of my triangle. That's the 5 meters. All right, as it does that, it has horizontal displacement of 4 meters and vertical displacement of 3 meters. Okay. All right, so with all of that in mind, let's solve this. Let's free up some space on the board here. So here we go. So our work done by non-conservative forces is, well, it's the work done by each of the non-conservative forces, which for us is the work done by Roy plus the work done by friction plus the work done by the normal force. And then we don't worry about gravity because that's conservative. Okay, remember, gravity is a conservative force. All right, so let's figure out what we get here. So the work done by Roy is, well, that's the force of Roy times the horizontal displacement, right? Because the force of Roy is horizontal. All we care about is the horizontal displacement. So for us, that's going to be 700 times 4, which is 2,800 joules. So that's the work from Roy. All right, and then the work from friction, well, let's see, the friction is parallel to the ramp. So I want the displacement parallel to the ramp. So, oops, force of friction, kinetic times displacement along the ramp. So that's negative 140 newtons down the ramp times 5 meters along the ramp. That's negative 700 joules. And then finally, the work done by the normal force is 0 because the displacement is parallel or perpendicular to the normal force, right? So that means the work done by my non-conservative forces is, what is that going to give you? 20, why does it do that? 2,100 joules. All right. So why do we care about this? Well, remember that 2,100 joules of work done by non-conservative forces is my change in GPE, KE plus my change in PE, right? So let's figure that out. So let's see. So we've got the work of non-conservative forces is my change in KE plus my change in PE. So I already know that this is 2,100. Let's find our change in potential energy. The only type of potential energy we've got here is gravitational. So my change in PE is my change in GPE, which is mg delta y or delta h, right? Which is, oh, well, that's just the 3 meters, right? So what do we got? A 40 kilogram box, acceleration of gravity is 9.8, delta y is 3 meters. Multiply this gives you 1176 joules. So 2,100 joules of non-conservative work is our change in KE plus 1176, the change in GPE. So the change in KE, if you figure it out, gives you a number 924 joules. And since we began at rest, this is just my final kinetic energy. So now I just do KE equals 1/2 times m times v squared. And you get a velocity of 6.8 meters per second. All right. So there we go. Now, you certainly could have done this by doing net force equals net force. You'd have to split Roy's force into components. You'd have to split gravity into components. It's a lot more trig. Debatable about which one's easier, but you could certainly do that. But there are definitely problems that you couldn't solve using net force equals net force, specifically if your acceleration is not constant. Okay, so let's do such an example. All right, so here what we've got is a spring, right? So the problem is, remember, with a spring, the force of a spring is changing, which means their net force changes, which means their acceleration changes, which means you can't do net force equals net force because your acceleration is not constant. So here we go. So what we've got this 4 kilogram block that's sitting here. So 4 kilograms. Let's start with purple. So we've got this 4 kilogram box that's sitting here against a spring. And as shown, it's in equilibrium. Okay, so this is kind of my initial position. All right. And so then what's going to happen is in part A, it says we're going to slowly squish the spring, compressing the spring, and then we're going to let go of the box, and the box is going to spring back up the ramp. All right. But question A is just about, as you squish the spring, how much work do you do? All right. But the problem is your force may or may not be constant because the force of the spring is not constant, right? So here's our initial point. So let's write down what we know about this initial point. Well, there's going to be a little bit of elastic potential energy, right? Because the sort of the weight of the block is compressing the spring a little bit. Okay. And so that, because it says it's in equilibrium. So here's the deal. So here's the block. it wants to slide down the ramp because of our parallel component of gravity, but the spring is holding it up, keeping it in equilibrium. Okay. So we know this is a 4 kilogram block, which means we can go through and, we know this angle here is 30 degrees. So we can find our forces. The force of gravity parallel turns out to be 19.6 newtons, which means the force of the spring must be 19.6 newtons. So now I'm just going to go, oh, well, force of the spring is negative K times X. 19.6 newtons equals 98 newtons per meter times X. Divide, your X turns out to be 0.2 meters. Okay, so that's my initial position. So let's make a note of that. So let's see, let's do this. Here, X is 0. Right now, I guess I should put, yeah, we do that. Right now, our X is at 0.2 meters. Yes, negative because it's down the hill, right? So let's figure out what our elastic potential energy is right now. So at this initial point, our elastic potential energy is 1/2 times K times X squared. So that gives you 1.96 joules worth of elastic potential energy at this initial point. Okay. Now, in part A, what we're going to do is we're going to take the spring and we're going to compress it another 0.3 meters to X equals 0.5. Okay, so the 0.2 plus the 0.3 gives us 0.5. So at our final point, we're going to have more elastic potential energy, right? Because when you pushed the box down, you stored more energy in that spring. So 1/2 times K times X squared. So the final elastic potential energy, if you figured out, is 12.25 joules. Now, remember, work is about change in energy. My elastic potential energy changed. There's probably going to be some value in finding that change in elastic potential energy. All right, so we'll do that in, I don't know, how about purple? All right, so our change in elastic potential energy is just final minus initial. So 12.25 minus 1.96. So that gives you 10.29 joules worth of elastic potential energy. Okay. Cool. So we're trying to find out how much work you did. So let's think about what forces are on the block. So here's the block. So there's the force of U, there's FG parallel, and there's the force of the spring. And then I guess FG perpendicular, which doesn't do work, and normal force, which doesn't do work. So it looks to me like the work done by non-conservative forces is just the work that you do, right? Because the spring and gravity are conservative forces. Okay. And that's equal to our change in total energy, which for us is our change in EPE plus our change in GPE plus our change in AE. Oh, cool. So if I just find my change in energy, I'm good. And I just found my change in EPE. Let's see, change in K is 0 because the block begins in equilibrium and then you're going to press it until the block stops again. So the change in K is 0. So the only other thing I need to worry about is the change in GPE. Let's do that in blue. So the idea is while we're compressing the spring, we compress it 0.3 meters along an incline of 30 degrees. So that means my change in height, if you SOHCAHTOA this, is 0.15 meters. So my change in GPE is mg delta H or delta Y, whatever you prefer. So what do we got? We got a 4 kilogram block. Acceleration of gravity is 9.8 meters a second squared. Change in height is 0.15 meters. Multiply this and you get negative, right? Because it's going down, 0.588 joules. Nope, lies. 5.88 joules is the change in GPE. All right. So that means then, almost out of room here, the work done by non-conservative forces, that's the same as the work you did, is the change in EPE plus the change in GPE plus the change in kinetic energy, which is 0. So this is, we gained 10.29 joules of elastic, but lost 5.88 joules of gravitational for a net change of 4.41 joules. So that's the work that you did. Cool. Now, I guess if you wanted to, you could now find the force that you exerted if your force was constant. All right. I guess we could even find the average force. So work of U equals force of U times displacement. So this really would be your average force. If your force is constant, then you're good. So the work you did is 4.41 joules. That's equal to your average force times your displacement, which was that additional 0.3 meters down the ramp. So divide both sides by 0.3, and the force of U average is whatever 4.41 divided by 0.3 is. This was a game time decision to do this problem. What do we get? Let's see, 4.41 divided by 0.3 gives you 14.7 newtons. All right. So if your force is constant, that's how much force you exerted. Otherwise, that's your average force. Wow. All right. A lot going on there. So let's suppose you let go of the block now. It's compressed. You're going to let it go. Let's see how far it goes up the ramp before stopping. All right. So now there are 2 points that I care about. So here's my initial point. So at this point, we know that our elastic potential energy is the 12.25 joules we just figured out. It's at rest. I guess we can call that a GPE of 0 if we want, right? That's the lowest point we're going to get to. All right. So now what we're going to do is we're going to let it go, chunk, and we're going to know how far is it going to go before it stops again. All right. Well, at this point, what do we know? Well, the EPE there is now going to be 0. The KE is now going to be 0. So we've just got some GPE that we didn't have before, right? Well, let's see. So once we let it go, the only forces are going to be the force of the spring and FG parallel, right? Which means there aren't any non-conservative forces. So the work done by non-conservative forces is 0. That means my change in mechanical energy is 0. Oh, so if the total energy here is 12.25, that means the total energy over here has to be 12.25 joules. So now I can find my height. So I'm going to go 12.25 equals 4 times 9.8 times height. Solve for the height, and you get a number that's written on a piece of paper over here, 0.3125 meters. Then you just consider your triangle. Oops, try that again. Just consider your triangle. Oh my goodness. So if this is 0.3125, then my hypotenuse, because this is 30 degrees, it looks like my delta x is going to be that divided by the sine of 30, which gives 0.625 meters. That's it on that one. All right, now, what if there was friction? What if there was friction? Bam, oops, blank page, bam. All right, so now what we're gonna do, let's suppose the ramp isn't frictionless, all right? Let's suppose the force of kinetic friction is 10 newtons. So kind of the same drawing. So we've got this point down here where our elastic potential energy down here is 12.25 joules. GPE is 0, KE is 0. We're going to let it go. Chank, boop, boop. There's going to be a point up here where the velocity is 0, kinetic energy is 0, EPE is 0, but we're going to have some GPE. Now our total energy is not constant because as the block slides up the ramp, we're going to have force of kinetic friction of 10 newtons. And then Fg parallel, and I guess the force of the spring for part of it, right? Now, the force of the spring is changing, the force of gravity is changing, but those are conservative forces. So here's what I'm going to do. I'm going to go, all right, well, the work that friction does, it's kinetic friction, I guess, right? That's the same as the work done by non-conservative forces. That's my change in mechanical energy, which is, it looks like the total energy at the top minus the total energy at the bottom. Cool. So what do we know? Well, the work done by friction is going to be the force of friction, negative 10 newtons, times this displacement. I guess we should label it. Let's call the distance that it goes delta x. All right, and then my GPE is the mass times 9.8 times my height. But again, I can use this triangle here. All right, we're going up a displacement of delta x. This is 30 degrees. Means the height is delta x over 2, just using some trig. Minus the EPE we started with. So I'm looking at negative 10 delta x equals 19.6 delta x minus 12.25. Add the 19.6 to both sides, and you get negative 29.6 delta x equals negative 12.25. Divide both sides by 29.6, and your delta x turns out to be, it looks like 0.309 meters. All right. So that's where our energy went, that's how far it'll slide. Okay. So it doesn't get quite as far, right? In fact, the spring doesn't even completely uncompress because the force of friction is so big. Okay. All right. All right. So notice the total energy at the top and the bottom is different, right? In fact, the energy that we lost, the work of non-conservative forces, our change in mechanical energy. Let's figure out what our change in mechanical energy was. So it's negative 10 times 0.309. So we lost 3.09 joules of energy. Where did it go, right? That energy has to go somewhere. Within the universe, we have conservation of energy. You can't just lose 3.09 joules of energy. So at the beginning of the video, I talked about thermal energy. That's where it went. Check it out. Where does friction fit into all of this? Well, it turns out that as a non-conservative force, there's nothing special about static friction, largely because relative to the moving object, it doesn't do work. Okay? But for kinetic friction, we can see that the energy lost turns into heat. Okay. So in this instance, we found that the work done by non-conservative forces was negative 3.09 joules. That's the same as the work done by friction. So that means that we gained 3.09 joules in thermal/heat energy. Okay. And you see this all the time. When you get cold, you rub your hands together, right? Think about it. When I'm moving my hand this way, friction pushes that way. My hands get warm, right? Gaining heat energy, but the entire time I'm pushing, friction's doing negative work. Okay. So the work done by friction is the opposite of the change in thermal energy. So I'm never going to worry about thermal energy unless the problem specifically says something about heat or thermal energy, in which case the change in thermal energy is the opposite of the work done by friction. Cool. Short of that, I'm going to be pretty sloppy about my mechanical and total energy, because if we're not worried about thermal energy, then the mechanical energy and the thermal energy are, for all intents and purposes, the same thing. All right. Oof. That was a tough video to get through. I guess we just did that last example. How much heat energy is created? 3.09 joules. There you go.